Alright, let's go ahead and start off here with a really quick review. Alright, so one of the things that we talked about on Friday, or maybe it was the last Wednesday's video, was this idea that you can take determinants of elementary matrices, and it's really easy to do so. So let's go ahead and let E be any elementary matrix. And remember, what an elementary matrix is a matrix obtained by performing one of the three elementary row operations to an identity matrix, to the n by n identity. Alright, so there's a couple things we can say. First off, we know there's three types of elementary matrices. Alright, and for each of these three types, we can easily determine the corresponding determinant of that matrix. Okay, so in the case when E corresponds to row swapping, so if E corresponds to row swap, then the determinant of E is just -1. Okay. Now, the second elementary matrix that we can look at is the elementary matrix obtained by multiplying a non-zero row by a constant. So let's go ahead and write that down. So if E corresponds to, we'll say, multiplication of a row by a non-zero constant, which we'll call Z. So a non-zero constant, we'll say C. Then that is actually what you get in the determinant. You just get C. So then the determinant of E is equal to C. Alright. And then the last one, of course, is probably the most common elementary row operation that we use, is where we take a multiple of one row and add it to another row. So let's say E corresponds to adding a multiple of one row to another row. So a multiple of one row to another. Then it turns out that the determinant of that corresponding elementary matrix is actually just equal to 1. Okay, so in particular here, you see that in each case, my determinant is not going to be 0, right? Because here, the determinant of E being equal to C, for example, we know C is restricted to be a non-zero constant. And so the determinant in particular is non-zero. And over here I have a typo. So in the first case, when E corresponds to row swap, the determinant of E is -1, not 1. Alright. So what we did here was sort of investigate this following result here. So we proved this fact in class, or in a video at some point. So the fact, there's two facts here. That if I take any matrix A and I sort of multiply on the left by an elementary matrix, then it turns out that the determinant of the product E multiplied by A is the same as the product of determinants. Yeah? And from that, you can deduce by iterating this result repeatedly that if I take a product of elementaries and multiply on the left by some arbitrary matrix A of size n, then this is equal to the product of determinants. So it's the product of the determinant of EK all the way until I get to the determinant of E sub 1, and then finally at the last slot, determinant of A. Determinant of A. Okay. So as long as I'm working with elementary matrices, the determinant enjoys this nice sort of multiplicative property. Alright, so let's go ahead and see what's on our agenda for today. Okay, so the first thing that I want to talk about is proving this multiplicative property in general. So we want to prove that the determinant, and remember we can view this as a function from the space of all square matrices of size n to the set of real numbers, is actually multiplicative. And I'll sort of illustrate what I mean by that. Multiplicative is multiplicative. All right. No. Let's go ahead and lastly, what I want to do is prove the final, like, sort of invertibility criteria. That this is probably the last one that we might talk about explicitly. There are others, but this is probably the last important one that we'll talk about. That the determinant of A not being 0, this is equivalent to saying that A inverse exists. Yeah? So this is an if and only if statement. A inverse exists if and only if the determinant is non-zero. All right. So let's go ahead and get started, and we'll talk about the multiplicative nature of the determinant. So go ahead and let me clear this up here really fast. Okay, so let's look at a quick example here. We've done an example similar to this, but it's worth sort of looking over again. Let's go ahead and let A be a matrix. This is going to be a 2 by 2 matrix. 1, 0, 0, 0, 2, we'll say. Yeah. And B is going to be another 2 by 2 matrix. It's going to be -1, 0, 0, -2. So it's just the negative of A. B is equal to the negative of A. All right, so these are square matrices. Of course, it makes sense to take their determinants, so let's actually do that. The determinant of A is just 1 multiplied by 2 minus 0 times 0. Remember, I'm using my formula here for the determinant of a 2 by 2 matrix. This is just equal to 2. And for the determinant of B, this is going to be -1 multiplied by -2 minus 0 times 0. Well, this is also equal to 2. So the determinant of A is equal to the determinant of B. Nice. Okay. Now, let's look to see what happens if we add A and B. So A added to B, of course, is the 0 matrix, right? Because B is the negative of A. Yeah? So, if I were to ask you to compute the determinant of A plus B, that's equivalent to taking the determinant of the 0 matrix, which we know is 0 times 0 minus 0 times 0. This is just 0, right? So in particular, we get this sort of following result here. We make this observation, that the determinant of A plus B is actually equal to what? We computed it. It's equal to 0. However, the determinant of A plus the determinant, we'll say plus the determinant of B is equal to 2 plus 2 is equal to 4, right? So in general, you see that the determinant is not additive, yeah? So these are not equal. These are not equal. Okay. And in general, this is true, that the determinant is not additive like this. So the determinant does not satisfy or enjoy a nice property of the form determinant of A plus B is equal to the determinant of A plus the determinant of B. Okay. However, the determinant is additive. I'm sorry, multiplicative. And let's sort of see that illustrated in this example here. So we know that the determinant of A multiplied by the determinant of A multiplied by the determinant of B, however, well, this is 2 multiplied by 2. This is equal to 4. Right? Now let's see what happens if we take the determinant of the product A and B. All right. So what I have to do is actually take the determinant of the product. So first I have to compute the product of A with B. All right. So A was the matrix 1, 0, 0, 2. B was the matrix -1, 0, 0, -2. All right. Okay. So it turns out that what we get here is the determinant of the 2 by 2 matrix. So you have to actually work this out on your own when you compute this product. What you're going to get is -1 here, and then I'll get a -4 down here. Yeah. And lo and behold, if you compute this determinant, what you're going to get is -1 multiplied by -4 minus 0 times 0. This is equal to 4. Yeah? So it turns out that these, in fact, in this case, are equal. Yeah, these are equal. Whoops. Yeah. So these are, in fact, equal. And this is this is true in general, that the determinant of a product is the product of determinants. And that's what I mean by the determinant being multiplicative. So that's actually a theorem, and we're going to take some time here to prove this. Okay, so what I'm going to do is take any square matrices. Of course, I have to take square matrices because otherwise the determinant isn't defined. So let A and B be matrices of size n by n. Okay. Then the determinant is multiplicative in the sense that the determinant of A multiplied by B is equal to the determinant of A multiplied by the determinant of B. All right, so let's actually prove this here. And you'll see it's not a terribly difficult proof. It relies heavily on the result I sort of stated at the beginning of class in our review about the determinant being multiplicative when you're looking at elementary matrices. Okay, so let's go ahead and write down our proof here. Okay, so we're going to consider two cases. Consider two cases. Okay. Okay, so the first case that we're going to consider is that A inverse exists. All right, so this, I should say, this is case one here. So case one is when A inverse exists. All right. So here I'm assuming that that A inverse exists. Okay. So if A inverse exists, which is what I'm assuming, then our invertibility criteria tells us that A can be written as a product of elementary matrices. Right. Right, because that was one of our invertibility criteria. So A inverse exists. That tells me that I can write A as a product of elementary matrices in this way here. Yeah. So is a product of elementary matrices, which I'll just abbreviate. Product of elementary matrices. Okay, nice. Now what I want to do is just resort to the result that we proved on Friday, or maybe it was in a video. Like I said, I can't remember. But what I can do is the following here. So in this case, the determinant of A multiplied by the determinant of B is really equal to the determinant of EK minus 1, etc., until I get to E sub 1 multiplied by B. Right? Here, all I did was replace A with its expression as a product of elementary matrices, which I know I can do because A inverse exists. All right. Now, I just resort to the result from the beginning of class, that this is actually equal to the determinant of EK multiplied by the determinant of E sub k minus 1, etc., multiplied by the determinant of E sub 1, multiplied by the determinant of B. Yeah. Okay. Now, it turns out that this here determinant, this is equal to the determinant of E sub k minus 1, etc., multiplied by E sub 1, but that is precisely the determinant of A. Determinant of A. Yeah. So lo and behold, altogether, we do get that the determinant of A multiplied by B is the determinant of A multiplied by the determinant of B. Okay. So that completes the proof in the case that A inverse exists. So now what we have to do is complete the proof in the case that A inverse does not exist. So this is our second case here. So this is case 2. We're going to assume here is that A inverse does not exist. Okay. So one thing that I want to recall again is another invertibility criteria that states that if A inverse does not exist, this implies that A is not row equivalent to the identity matrix. So is not row equivalent to the n by n identity. Okay. So if A is not row equivalent to the n by n identity, that tells me that the row reduced echelon form of A has a row of all zeros. Okay, so let's call the row reduced echelon form of A, we'll call it C. We'll just call it the matrix C. Okay, so C is what I'm defining to be the row reduced echelon form of A. Now, of course, I can't use B here because B is already used. That's why I called it a C. Okay, so the matrix C, which I'm defining to be the row reduced echelon form of A, has a row of zeros. Has a row of zeros, of all zeros. Okay. Now, what I want to do is use the fact that, there's this nice relationship between row reduction and multiplication by elementary matrices. So there are elementary matrices, we'll say E sub k. Wait, hold on. I'll just start labeling them like this. So E sub 1, E sub 2, etc. E sub k, such that I can obtain C from A by multiplying on the left by these elementary matrices, such that C can be written in the form EK, etc., all the way until I get to E sub 1 until I get to A. Okay. So what that implies here is that, what does that say? That tells me that A has an expression in terms of elementary matrices as, what do I get? Yeah, it's going to be E1 inverse, and then E2 inverse, all the way until I get to E sub k inverse, and then I multiply by C. Okay. Now, elementary matrices are elementary. So therefore, we know the following fact here. So the determinant of A multiplied by B, well, I use this representation for A. This is the determinant of this huge product, E1 inverse, E2 inverse, etc., until I get to E sub k inverse, until I get to C, and then I multiply by B. Yeah. Now, the inverse of an elementary matrix, well, not only does it exist, but it's also an elementary matrix. So I can use the result from the beginning of class to say that this is the determinant of E1 inverse multiplied by, wait 1 second, what am I doing here? Yeah, multiplied by the determinant of E2 inverse, etc., until I get to the determinant of E sub k inverse, and then finally I get to the determinant of the product of CB. Yeah. So here I'm using the result at the beginning of the class. All right. Now, C has a row of all zeros, so C multiplied by B is also going to have a row of all zeros. All right. So therefore, this determinant here is equal to 0. So in the overall product, this is also going to be 0. Yeah. I don't care what the determinant of these elementary matrices are because I'm multiplying them by 0. So the determinant of A multiplied by B is equal to 0. Yeah. On the other hand, so let's write this out. So on the other hand, the determinant of A multiplied by the determinant of B, well, this is equal to the determinant of A. What was A? A, remember, could be written as E1 inverse multiplied by E2 inverse, etc., until I get to E sub k inverse multiplied by C multiplied by the determinant of B. Here I just replaced A with its expression. And then now I can again use the result from class, from the beginning of class, to say this is the determinant of E1 inverse multiplied by the determinant of E2 inverse, etc., until I get to the determinant of E sub k inverse multiplied by the determinant of C multiplied by the determinant of B. C is the row-reduced echelon form of A. It has a row of all zeros, so this is also 0. This term here is 0. So the overall product is, of course, 0. Right? So I just proved that the determinant of A multiplied by the determinant of B is 0, and I proved that the determinant of the product of A and B is also 0. So that proves the claim. Yeah. So in general, you always have multiplicity of the multiplicativeness of the determinant. The determinant of a product is product of determinants. Okay, yes. And then at the beginning of class, I think on Monday or tomorrow, I'll show you a really nice application of this fact that matrices are, that the determinant is multiplicative. We'll look at a really nice example. Okay. So the next thing that I want to do, and actually this is the last thing that I want to do. It's not going to be a terribly long video, I don't think. I do want to talk about, what did I want to talk about? Yes, this equivalence between the determinant being non-zero and the existence of the inverse of A, right? So we're looking at more invertibility criteria. Now, we've mentioned this in passing, but right now I'd like to actually prove it here. So this is a theorem. Okay. Now it says that it says the following. So I'm going to take an n by n matrix. So let A be any matrix of size n, because I'm going to want to take its determinant. And to do that, I know I need a square matrix. Okay, so the result is the following, that the determinant of A is not equal to 0. Saying that is equivalent, so this is an if and only if A inverse exists. A inverse exists. All right, so let's actually prove this. And again, since this is an equivalence of statements, I have two directions that I have to prove. So here's my proof here. All right, so let's first prove that A inverse existing implies that the determinant is non-zero. So let's suppose A inverse exists. All right. So here I'm proving the direction, the reverse direction here, as I've stated it. So I'm supposing that A inverse exists. I want to prove that the determinant is non-zero. Okay. Suppose A inverse exists. What can I say? I know by my invertibility criteria that A can be written as a product of elementary matrices. Then A is the product of elementary matrices. Elementary matrices. All right. In particular, what I can do is write A in the form, we'll just say E sub k minus 1, until I get to maybe some E sub 2 and then E sub 1. Okay. What I can do now is take the determinant of A. And remember, my goal here is to prove that the determinant of A is non-zero. So the determinant of A is the determinant of this product. Yeah. But we know that the determinant is multiplicative, right? So this is equal to the determinant of E sub k multiplied by the determinant of E sub k minus 1, etc., until I get to the determinant of E sub 2, and then the determinant of E sub 1. Okay? Now, the determinant of an elementary matrix is non-zero. Remember, I pointed that out during our review, that in each of the cases, remember there's 3 cases that you have for elementary matrices. It either corresponds to a row swap, multiplication of a row by a non-zero constant, or possibly by adding a multiple of another row, or of one row to another row. But in each of the cases, the determinant was non-zero. So here I'm taking the product of k non-zero numbers. So the product is non-zero. Non-zero. Okay? So I proved the direction that I wanted to prove. I assumed that A inverse existed, and I concluded that the determinant of A was non-zero. All right, so that proves one of the directions. Okay. The next direction is where I suppose that the determinant of A is non-zero, and I want to prove that A inverse exists. Okay. The way I'm going to do that is by proving the converse statement. I'm going to suppose A inverse doesn't exist, and I'm going to prove that the determinant of A has to be zero. Okay. And now we have to prove the reverse direction. What I want to do in proving the reverse direction is, of course, proving that if the determinant of A is not zero, then A inverse exists. Okay. So my goal now is to prove that if you assume that the determinant of A is non-zero, then the determinant must exist. Okay, so what I'm going to write down is the following. So to prove determinant of A not zero implies that A inverse exists, we're going to actually prove this by proving the converse statement. So we prove the converse statements. So we're going to prove that A inverse does not exist implies that the determinant of A has to be zero. Okay. All right. So we're going to prove that A inverse not existing implies that the determinant of A has to be zero. All right. So let's prove that. Okay. So suppose A inverse doesn't exist. So if A inverse does not exist, then we know that A is not row equivalent to the identity matrix. Is not row equivalent to the n by n identity matrix. Okay. Therefore, B, which I'm calling to be the row reduced echelon form of A, has a row of all zeros. Row of all zeros. Yeah? And what we can do is, once again, use the relationship between Gauss-Jordan elimination, or row reduction, if you will, and multiplication by elementary matrices. So we can write A in the following form. We can write, B in the following form. We can write B is equal to E sub k multiplied by E sub k minus 1, etc., until I get to E sub 1 multiplied by A. Right? Okay. So what I get here is the following. I can actually take the determinant of both sides. All right. So the determinant of B is equal to the determinant of this right-hand side, E sub k, etc., E sub 1 multiplied by A. Okay. Now, the determinant, oh, wait, one second. Okay, so let me use the fact that determinant is multiplicative again. So this is the determinant of E sub k, etc., until I get to the determinant of E sub 1. And then at the last, I'll get the determinant of A. Okay, so B has a row of all zeros. Therefore, I know that this determinant of B is equal to 0, right? Now, one thing you'll notice is that the determinant of an elementary matrix, once again, this is not 0. None of these determinants are equal to 0, right? So the only way for this product of real numbers to be 0 is if the determinant of A has to be 0, yeah? So this must be equal to 0. Must be 0. All right, and that proves the claim. That proves that if A inverse doesn't exist, then the determinant of A has to be 0. And that proves the theorem overall. So that's our theorem here. And it adds to our invertibility criteria, our list of nice invertibility criteria. So let's go ahead and, just to remind ourselves what those criteria were. So this is our list of invertibility criteria that we have so far. And like I said, these are like sort of the most important ones, I'd say, invertibility criteria. We may introduce more at some point, but these are certainly ones that I would keep in mind. Okay, so let's do the following here. Okay, so again, all of these statements are equivalent. So the following are equivalent statements. All right. So on one hand, the existence of A inverse. A inverse exists. Remember, the way we introduced the second criteria at first was by saying the following. The only solution to the equation ax equals to the 0 vector is the trivial solution where we say x is equal to 0, right? And then what we did is we sort of recast this in terms of the null space of A by saying that the null space of A is actually the 0 vector space. It is the trivial vector space. Okay. Now in part C, what we have is A is row equivalent to the n by n identity. Row equivalent to the n by n identity. All right. And then the fourth sort of criteria that we talked about was the expression of A as a product of elementary matrices. So A is the product of elementary matrices. Yeah. And then what we did is we went on and we sort of proved that that we can add a fifth criteria here by saying that A has full rank. In other words, that the rank of A is equal to n. Here, n is the size of the matrix. A is an n by n matrix. Yeah, i.e., A has full rank. Okay, and then now we have a sixth criteria that says that the determinant of A is not equal to 0. Okay. So let's look at a really quick example, and then we'll call it a day here. Okay. So what I'm going to do is define a matrix for us. We'll look at a 3 by 3. 1, 1, 2, 3, 0, 1, 2, 0, 3. Wait, no, I want 0, 0, 0 on the last. And the last place, 0, 0, 0. Okay. So I know that the determinant of A is going to be 0 because it has a row of all zeros, right? So in particular, this matrix does not have an inverse. Does not exist. Yeah. And I determined that, in a really easy way. Some more invertibility criteria. Okay. All right, yeah, so that does it. Like I said, on tomorrow on Monday, we're gonna talk more about elementary. Not elementary matrices. We're gonna look at an example of the application of the multiplicative nature of the determinant. That shouldn't take long. Then after that, we'll go back to talking to nothing about linear maps.